Let's talk about the energy requirements for changing the state of a substance. Let's remember that state changes are physical changes. No chemical bonds are broken. The substance is the same substance. Now, it may look different, right? Steam looks a lot different than ice cubes. But the individual particles are still the same. There's these little red and white Mickey Mouse heads, right? That's our common representation of water molecules. So when we're boiling water here, this is in the liquid state, and as it boils, it moves into the gas state, but the individual particles are not changed. And that's what distinguishes a physical change from a chemical change. In a chemical change, the water molecules would be destroyed and different particles would be formed. Okay, so a lot of state changes, you can just think about it. You know, you cut a piece of wood in half, or you cut a piece of copper metal in half. Okay, so you've made the pieces smaller, but the individual atoms are the same. And we can think about that and reason that through. The state changes, it's not as immediately obvious, but I've told you before, and I'm telling you again, physical change for state changes. Melting, freezing, boiling, condensing, subliming, all those state changes are just physical changes. Well, let's go back here for a minute. Why is the water a liquid here, and then when we heat it up, it's a gas and it flies away? What's the difference? The molecules are the same. Why is the water sticking together here? Why is ice hard and rigid, and liquid water is fluid? It's a liquid. It moves, right? You know, jumping into a swimming pool full of liquid water is a much more pleasant experience than jumping into a swimming pool full of solid water, right? What's the difference? The molecules are the same. Well, it has to do with intramolecular forces, intermolecular forces. So here's some prefixes. There are different sorts of forces. Let me get back to the correct color here. Intramolecular means within the molecule. These are the bonds that are holding the molecule together. Okay, we looked at Lewis structures, and we learned that we can represent water like this. This covalent bond between the hydrogen atom and the oxygen atom is an intramolecular force. It's within the molecule. Intramural sports. You're playing against teams of students who attend the same school, right? You're all in the same school. Intramural, you're just playing between each other. Intercollegiate sports means you play a team of students attending a different college, right? So there's inter and intra. Intra is within, inter is between. So the intramolecular forces are what hold the atoms of the molecule together. The intermolecular forces occur between the molecules. And I'm looking at this and I'm thinking there's that big space in the middle. Oh, okay, good. I just missed deleting an animation. Looks like there's supposed to be a picture there. There's that picture. So here with water again, these bonds between the hydrogen and the oxygen atoms inside this molecule are the intramolecular forces. We usually call those bonds as opposed to intramolecular forces. But then there are also forces of attraction between adjacent water molecules. These are the intermolecular forces. And those are what have to do with boiling point and freezing point and all sorts of other things. Intermolecular forces. Well, what are these forces? Let's make sure there's no pictures. Okay, no picture on that slide. There are three different kinds of intermolecular forces. So one of them is called a dipole-dipole force, and we're going to talk about what these are. A second one is called hydrogen bonding. Hydrogen bonding is actually a special subcategory of the dipole-dipole forces. And then we have another one called London dispersion forces. Do you remember what a dipole is? Something that has two poles, and we can get that just from the name. Dipole, di meaning two poles. The ends are different. So it's a molecule that's lopsided in terms of electrical charge. So, like a molecule like hydrogen fluoride. We talked about electronegativity and how fluorine is the most electronegative element. It hogs the electrons that are in this shared bond, and here's hydrogen, and so this end is slightly negative, this end is slightly positive. This molecule has a dipole. A dipole-dipole force is the attraction between two dipoles. Hydrogen bonding is like dipole-dipole forces on steroids. It's extreme dipole forces. So all of these intermolecular forces are electrostatic in nature, meaning it has to do with electrical charge. Opposite charges attract each other. As charges get farther apart from each other, they become weaker. And I'm just wondering, is there anyone who has not played with magnets at some point in their life? Anybody? Magnets are fascinating, aren't they? I mean, even just the refrigerator magnet, and you're like, wow, it sticks, and it'll hold up one piece of paper, but it won't hold up 10 pieces of paper. Why? Because the 10 pieces of paper are too thick and keep it too far away from the surface of the refrigerator. The attraction, the force of attraction of electrostatic and magnetic fields behave very similarly. And so as the magnets get farther apart, the attraction gets much weaker. And the same is true with electrostatic attractions. So when you get them very far apart, they get very, very weak. So let's look at these. So the first one we'll look at is a dipole attraction. So these kind of look like little grains of rice or something. This is a molecule that has a dipole. One end is slightly negative, one end is slightly positive because the electrons are not being shared equally. Well, the positive end of this molecule is electrostatically attracted to the negative end of that molecule. And so when you get a whole bunch of them together, here these are color-coded, there are red lines and blue lines. And so the red lines are forces of attraction between opposite charges, and there are also forces of repulsion between like forces. So these two positive ends are going to repel each other, the positive and negative are going to attract each other. And in a liquid, and this is a representation of a liquid, you've got these molecules all jumbled up, and so you have a mixture of these forces of attraction and forces of repulsion. So we say that a molecule that is polar, a polar molecule has a dipole moment. And that's because molecules that have polar bonds often behave as if they had a center of positive charge and a center of negative charge. I should actually find a video of this and show you because it's kind of cool. I'll draw you a dumb picture of it instead. So here's a faucet. And here's, I guess we should make water blue, right? There's water coming down. If you put a magnetic field or an electrostatic field across the water, you can actually make the stream of water move over without touching it. You can just make it move over. It's really awesome. It's crazy looking. It looks like magic. But it's because water is a polar molecule. And when you apply an electric field near the water will be attracted to one side and repelled by the other side. So polar molecules, molecules with dipole moments behave that way. Molecules with dipole moments can attract each other, like we looked at in the previous slide. Now it's important to understand these dipole forces are weak. Typical dipole-dipole forces are 1% as strong as an actual bond. So these forces are significant, but they are much weaker than the actual bonds. Nope, okay. I don't trust my slides today. So hydrogen bonding is just a special word for really strong dipole-dipole forces. And this happens when we have an especially polar situation. And this occurs when we have hydrogen bound to a very highly electronegative atom, such as nitrogen, oxygen, or fluorine. Remember on the periodic table we said fluorine was the most electronegative. Oxygen and nitrogen are right next to it. They are the two next most electronegative elements. And so here's one way to remember those guys. Have you seen the movie E.T.? At least heard of E.T.? And what did E.T. keep saying? He pointed at the sky. E.T., phone home. Phone home. Okay? F, O, or N bonded to hydrogen. If you see that in a molecule, it's going to have hydrogen bonding. Okay? So you can just remember E.T. phone home. Here's a picture. In water, water's a polar molecule, and it has a hydrogen-oxygen bond. It actually has two hydrogen-oxygen bonds. And what's special about these is that oxygen is very electronegative. And so remember we talked about there being a partial charge. So there's a partial negative charge on the oxygen and a partial positive charge on the hydrogen. It's less than 1. But how much of 1 is it? Is it half or 0.25 or 0.01? What is that partial charge? Well, we don't care exactly. But when we have a large difference in electronegativity, like there is between hydrogen and oxygen, this partial negative charge is greater, and the partial positive charge is greater than if you have, say, like if you have nitrogen, oxygen, those are right next to each other. The electronegativity difference is smaller. The larger the difference, the larger the charge. It's a partial charge, but the larger the partial charge. So we have a molecule here with an OH bond. That means we have the potential for hydrogen bonding. And so it is just this dipole force, dipole-dipole force between the oxygen on one molecule and the hydrogen on the other molecule. And it has a special name because it's extra strong. So this is just showing how the water molecules will hydrogen bond with each other. And this hydrogen bonding explains a lot of the strange properties of water. One of these properties is boiling point. If you haven't noticed yet, scientists like to graph things, okay, because it's a way of taking numbers and making a picture out of them, and because it's hard to just look at numbers and see what's going on. When you graph them, you can see better what's going on. So what do we have going on here? Here we're graphing the boiling point of the substance as a function of its period in the periodic table. So we're doing compounds H2 and some element. So here's H2O. Oxygen is in period 2. And if we're just going down that column, there's sulfur and selenium and tellurium. So tellurium is over here because it's in period 5. So we're graphing the boiling point of these substances as a function of their period. And these three out here are making a relatively straight line. Do you see that? It's not perfectly straight, but it's definitely a trend. Let's see if I can draw a straight line. Something like that. There's a trend there, right? Do these molecules have hydrogen bonding? They all have hydrogen. Can you say ET phone home? They don't have fluorine, oxygen, or nitrogen, do they? So these have dipole-dipole forces, but they don't have the extra strong dipole-dipole force we call hydrogen bonding. What about water? Does water have hydrogen bonding? It does. Look at the boiling point of water. If we were going on this trend here, we would predict that the boiling point of water would be around minus 100 degrees. If that was true, there would be no liquid water on Earth, because regular temperature is around 20 to 30 degrees Celsius. The water would all have boiled. But water has a boiling point that's way up here at 100 degrees Celsius. And that's because it has extra strong forces holding the particles together. I wish I could remember where these slides are going. Just going to sneak a peek. Okay, I guess we'll get to it over there. Okay, so London dispersion forces. And this group of forces has lots of names. Your book calls them London dispersion forces. Some books call them London forces or dispersion forces. Other books call them induced dipole forces, which is a name that I prefer because I think it's more descriptive. I mean, it's nice to honor Mr. London. That's not for the city, it's for a guy whose name was London. It's nice to honor him, but it doesn't help students very much. London dispersion forces happen between instantaneous dipoles. So you can have an instantaneous dipole that occurs, we can think of it as being accidental, an accidental imbalance of electrons. And when that happens, it can induce or cause to form a dipole in the neighboring molecule. So if we look at this picture down here, here's atom A and atom B, and these are nonpolar. They're just atoms. They're not sharing electrons with anybody, so they have to be nonpolar. But what if the electrons in this atom happen to be more on this side than on the other side? Because atoms are very random little things, kind of like my son Andrew. They're just, kind of all over the place. And so they could all be kind of bunched up on one side, just sort of by accident. It's a little bit like taking a cruise in the San Francisco Bay. You just get blue and white cruises, and you go out and you on this big boat, and you go around Alcatraz, right? And so before you get out to Alcatraz, everybody's kind of spread uniformly around the boat. And then you get near Alcatraz, and everybody goes to the Alcatraz side of the boat, right? They're like, oh, look, that's what we came out here to see. And then the boat gets just a teeny tiny bit lopsided. Unless they've, overloaded it and violated safety regulations and stuff. It's not going to actually list and tip over. But it gets a little bit off balance when all the people happen to be on one side. Is that a normal state for all the people to be on one side? No, they're not going to all stay there either. They'll go back to being more spread out. But that happens with electrons. They are moving around within the atom, and they can do pretty much anything they want to. And so they can be just spontaneously, accidentally, kind of lopsided. Well, what happens then is that you have a positive side and a negative side, just like in a polar molecule. And that has an effect on the atom next door. Because the electrons in this atom are repelled by this positive charge. They're like, oh, positive charge, let's go to the other side of our atom. And so they go to the other side, and then we get this, no, I'm sorry, I did that backwards. These Pluses and minuses are so small I'm having a hard time seeing them. This is positive. The positive side attracts the electrons, just like the Alcatraz attracted the people. And so the electrons in atom B are drawn to this side, and this atom also gets lopsided. We call that an induced dipole or an instantaneous dipole. It's not going to stay that way. A polar molecule always has a dipole. So the dipole-dipole forces, those are permanent dipoles. These are temporary spontaneous dipoles. But a spontaneous dipole in one induces a dipole in the other, and now we have a very brief interaction between these two atoms. And these London dispersion forces occur in all substances. Everything has London dispersion forces. They occur in all molecules, including nonpolar ones, including atoms. Because how is it that we can have a solid of an element? It's formed of atoms. They're all nonpolar. How can they stick together? You know, when we look at the nonmetals, iodine is a solid at room temperature. I did an experiment for you, a demonstration where we took the iodine crystals and heated them and sublimed them. Do you remember that? Made a purple gas. But at room temperature, iodine is a solid. It is diatomic. It's I2. But we have two identical atoms bonded to each other. There's no polar bond there. There's no permanent dipole. How can this be a solid? How can those molecules stick together? It's because of these induced dipoles. These London dispersion forces are more significant in larger atoms or molecules. The larger the atom or molecule, the stronger the London dispersion forces. I think of it this way. If you have a really large atom with a lot of electrons, it's kind of like a big family. And a big family with lots of kids, it's more likely that things will get a little bit lopsided than if you have a really small family and those kids are very close. And so then they're going to be more equally distributed. So these big, larger elements like iodine, the intermolecular forces from the strength of the London dispersion forces is greater because those electrons can move back and forth more easily. They're farther from the nucleus, and so they can get lopsided more easily. It's kind of a rambling explanation. Here's a larger picture, which is probably what I should have used in the first place. Let's look at a hydrogen molecule. Two hydrogen atoms. Is this a polar bond or a nonpolar bond? Is polar. The two atoms are identical. So the electrons that they share are going to be shared equally. But they can spontaneously be off a little bit. And so here we're showing that the electrons by this darker blue over here are more around this hydrogen atom right now and less around this one. That's an instantaneous dipole. And then this slight positive charge here attracts the electrons in the neighboring hydrogen molecule and causes this one to get unbalanced also. And then there is an attraction between these two guys. So we were using dotted lines earlier. So now we have a force of attraction between the positive end and the negative end. But then the first atom regains its equilibrium, you could say. It goes back to being nonpolar. The electrons spread out again. And then this force goes away. And so these forces are very brief. Very brief. They don't last very long. But they happen a lot. And so they do become significant. We can see that by looking at or comparing freezing points of elements in a group of the periodic table. So these are the noble gases, and this is going down the periodic table: helium, neon, argon, krypton, xenon. As we're going down, the the mass of these is getting larger, the size of them is getting larger. Xenon has a mass of 131, helium has a mass of 4. And what do we see happening with the freezing point? Helium will freeze at minus 272 Kelvin, but only if you put 25 atmospheres of pressure on it. Neon will freeze at minus 248. Argon freezes at minus 189. The freezing point is increasing, right? That shows us that the force of attraction between these particles is becoming greater. I feel like there's something missing here in this explanation. So let's think about a solid. So here's my really sad solid. Why are these atoms staying together in a solid? What's holding them together? Some kind of force between molecules. It could be polar attractions if these are polar molecules. It's one of these intermolecular forces, right? The intermolecular forces are holding them together. All particles, though, are moving, even the ones in your bench or your desk, but they're vibrating. Remember I gave you the illustration of solid, liquid, and gas states of students. Right now you guys are in the solid state. You're all sitting in your chairs. You're not milling about the room. But are you moving? Yeah. You're nodding your head. You're yawning. You're, taking notes maybe. Everybody's breathing. That's a good thing. You're moving. When we increase the temperature of a solid, temperature is a measure of kinetic energy. When we increase the temperature, these molecules are vibrating and moving faster. They're wiggling and you can think of them as getting agitated. And what's holding them together? Those intermolecular forces. If they get enough kinetic energy, they can break those intermolecular forces and move apart from each other. Now, when it moves away from, like this guy right here, he's being attracted to the ones around it. When he has enough energy to get away from those and move, he's going to be attracted by other ones, and so he's not going to fly off into the gas state, but he's going to be able to move. So as we increase the temperature, they're able to break the intermolecular forces. So temperature of melting or freezing gives us a picture of the strength of the intermolecular forces. If the forces here are very weak, then you only have to heat it up a little bit to get it to melt. Does that make sense? And if the forces are really strong, these guys are going to have to really get agitated to break away from each other. You think of it as being a little bit like Velcro. So if you have, objects that are like covered in Velcro, like those walls where you put on a Velcro suit and you jump, right? And it holds you up there, right? But then there are other, if you have just a little dot of Velcro on your sleeve and you bump against the Velcro wall, is that going to support your body weight? No, because that's a weaker force. So to break that weak force takes just a little bit of action, but to break a strong force takes a lot of action. So weak intermolecular forces, low melting point. Melting point and freezing point are really the same thing. It's just an idea of which direction you're going. So neon would melt at minus 248 Celsius. It's really cold. Xenon melts at minus 111. Still really cold, but that's a higher temperature than where neon melts. Which means that to get xenon to melt, you have to have a lot more energy. The forces of attraction between the molecules or the atoms are stronger. So what's different about helium and xenon is that xenon is larger. Larger molecule, stronger London dispersion forces. Larger molecule, higher freezing point, melting point. Did that make any sense? So in general, the stronger the intermolecular forces, the higher the melting and boiling points. This is why water in that graph had such a crazy high boiling point. So we had these guys over here, and then water was way up there, and here's this trend, and this is where we expect water to be, but its boiling point is actually up there. Because boiling is just going from a liquid to a gas, and again, you are having to break intermolecular forces. If they have stronger stick-togetherness, you need a higher temperature to break that, because high temperature reflects higher movement. And so water having the hydrogen bonds, which are the strongest of the intermolecular forces, it has an unusually high boiling point. This one was tellurium. There's this trend here is because tellurium is a larger atom. It has stronger London dispersion forces than selenium and sulfur. And so we would expect oxygen to be lower based on that trend in molecular mass or size. Okay, so which molecule is capable of forming stronger intermolecular forces? N2 or H2O? Well, let's look at N2. What kind of a molecule is this? Does it have a positive and a negative end? Is it polar? Is there any difference between this nitrogen atom and that nitrogen atom? They're the same, right? So this is a nonpolar molecule. Is this going to have hydrogen bonding? It doesn't even have hydrogen in it. ET phone home, hydrogen bonding. In order to have hydrogen bonding, you have to have hydrogen. If there's no hydrogen, forget it. Hydrogen bonds are the most strong, and the dipole-dipole forces are in the middle, and the dispersion forces are the weakest. In order to have the dipole-dipole forces, you need a permanent dipole. This doesn't have a permanent dipole. So all it has are those London dispersion forces. Let's call them LDF, London dispersion forces. Well, water. That's got a hydrogen in it. Could this have hydrogen bonding? Yes. So water has hydrogen bonding. It's a polar molecule, and it's got those OH bonds. So which of these has stronger intermolecular forces? The water. Let's look at these Lewis structures. These both have the formula C2H6O. The atoms are just arranged a little differently. And I wouldn't expect you to come up with these, so that's why I drew them for you. Let's just look at these. Is this molecule lopsided? Does it look lopsided? It does. It's not really symmetrical, right? Because this end has this OH and this end doesn't. So what's our best guess? Is that polar or nonpolar? That's probably going to be polar. What about this one over here? Is that one lopsided? Not really, right? There's an oxygen in the middle, and then both sides are the same. Turns out this one's a little bit polar, but not nearly like the other one. So we can basically call that nonpolar, which is what I would expect you to come up with. So just looking at that, polar versus nonpolar, which would you expect to have a higher boiling point? Think about, in order for something to boil, the particles have to get up enough kinetic energy to break loose. So if it's got stronger forces, they have to be moving faster in order to get out. Which of these has stronger intermolecular forces, the polar one or the nonpolar one? The polar one, right? Because all polar molecules have dipole-dipole forces. Do you think this molecule has hydrogen bonding? Yeah. We've got a hydrogen-oxygen bond. So this is a polar molecule, so this has much stronger intermolecular forces. This has the hydrogen bonding, the London dispersion forces, and the dipole-dipole forces. This guy, being nonpolar, pretty much just has the London dispersion forces. The oxygen in the middle makes it a teeny tiny bit polar. So to compare the boiling points, we can say this one has a higher boiling point, and this one has a lower boiling point. Because the forces of attraction between these molecules are greater than the forces of attraction between these molecules. Any questions? Can't remember if this is the last slide. Oh, we don't want to do that one. Let's do this one. Look at these compounds. How many of them exhibit London dispersion forces? Three. It's kind of a trick question. All substances have London dispersion forces. So the answer would be D, all three of them. All substances have London dispersion forces. Substances can have more than one kind of intermolecular force. So water has London dispersion forces and dipole-dipole forces and hydrogen bonding. Now if we look at these guys, ammonia has a lone pair on the central atom, and so we learned that that would be polar. So this would have dipole-dipole forces also. Here with methane, it's a carbon with 4 hydrogens around it. There's no lone pairs on the central atom, and all the atoms bonded to it are the same. So this is nonpolar. That means that it only has the London dispersion forces. And then this guy, H2, 2 identical atoms bonded together, that's also going to be nonpolar. So 2 of them only have London dispersion forces, but they all have London dispersion forces.